Hello, everyone. It's a great pleasure to be here today. My name is Senwei Liang, and I'm a postdoc from the Scalable Solver Group under supervision of Professor Chao Yang. Today, I'm going to present our research on discovering the reaction channel with reinforcement learning. We are interested in the chemical reaction that happened during the time evolution of molecule, and this reaction are the dynamical process that characterized by the transition from one stable state to another stable state. And these transitions are rare, but it's crucial in many applications. And for the transition to occur, the energy of the molecule must cross the energy barrier and evolve from one local minimum of the energy to another local minimum of the energy. And one way to study this transition is through the direct numerical simulation. However, the regular numerical simulation is both expensive and impractical to observe the transition. For example, to observe the ionization in water molecule, and one needs to conduct the numerical simulation for 1 femtosecond per integration step, and with a total about 10 to 18 numerical steps to observe the transition. This is not possible for any computer to handle it within a reasonable time. Despite this, studying the transition provides some invaluable insight into the mechanism of the reaction. And we can have a wide range of the application in the fields such as biochemistry, material science, and chemical engineering. And by better understanding the mechanism of this reaction, we can make strides in the areas such as understanding the conformation change in large molecule and studying the chemical kinetics in the complex system, and also designing some new drugs and materials. Okay, exploring the energy landscape of the molecule provides an important approach to study the transition. However, the challenges lies in the high dimensionality of the configuration space. For instance, for the molecule with n atoms, then the dimension is 3 times n in Cartesian coordinate. And many methods has been proposed to address this problem. For example, some people will use the transition path sampling to generate an ensemble of the reactive transition paths from between two stable states. And some people will aim to find some important points on the energy surface, such as the center points. And some people will also use the so-called collective variables to decrease the dimensionality of the high dimension configurations to some low dimensional features. But this method usually requires some prior knowledge of the system. And without much prior knowledge of the system, we want to develop an algorithm that can automatically to identify some important regions, and we call the reaction channel. And the reaction channel is some region in the potential surface that and where the transition happen most probably. In our basic workflows, and we want to find some intermediate point in the transition regions called the kinetic configuration. And this kinetic configuration is the configuration that has a high probability of observing the transitional path crossing it. And we will use the reinforcement learning to search for this kinetic configuration with the power of the reinforcement learning to explore the environment and also handle some uncertainty. And after that, after we find some kinetic configuration, and we can choose some trajectories from these kinetic configurations, and we can characterize the reaction channel using these trajectories. And further, we can using the configuration we find to do some computer analysis and compute the reaction rate. Before we dive into the our algorithm of discovering the reaction channel, I want to quickly to explain what reinforcement learning is. And reinforcement learning is a type of the machine learning that where the agent is trained to make decisions by maximizing the reward during its interaction with the environment. And the agent observes a state from the environment, and then it takes an action. And then the environment will respond and change to a new state and give the reward feedback to the agent. And the classical environment is the video game, and this environment contains a lot of the uncertainty and stochastic elements. And we use the term tau to denote one round of the game, and use the R tau to denote the total reward during playing the game before the game ends. And the objective for the reinforcement learning to play the video game is to they want to find the policy pi that can maximize the cumulative reward. And we have seen numerous examples of the reinforcement learning to praise the video game and delivering some outstanding performance and even outperforming the human being, for example, the AlphaGo. And this highlights some potential of the reinforcement learning to apply our problem to discovering the kinetic configuration. Okay, one may wonder how can the reinforcement learning to be applied to our problem of identifying discovering the reaction channels. And our objective is to find the kinetic configuration with high reactive probability. And however, the reactive probability is not directly accessible, but we can still estimate it through the shooting. Suppose we given the configuration S, and we shoot n trajectory from this configuration, and we counted number of the NA shot, number of the shots NA, reaching the state A first, and NB to the number of the shootings reaching state B first. And then we can define the reward at the configuration S by this one. And this reverse consists of two parts. And the first components emphasize the importance of finding the configuration that has the balanced probability to reaching either state A or either state B. And the second one is the stationary density that highlights that we want to find the configuration that should be easily to observe. But however, this reward is highly uncertain due to the nature of the random shooting. And even with the same configuration S, we will have the different value of the S. So we basically need to have a number of shooting N should be sufficiently large to get a very accurate estimation of the reactive probability. But with reinforcement learning, we can still use not that large N to estimate the reward. And then we formulate the problem of finding the kinetic configuration as a game. And we define the game environment as follows. And we start from the random configuration, and then we evolve the configuration by the policy parameterized by the neural network. And the input of the neural network is the current configuration, and the output of the neural network is the vector. And then we can get the new state by adding the current state ST and also the new the vector AT. And after we get the new configuration and we put it in the reaction environment and then compute the reward through the shooting. Okay, now let me show how effective our method is with two numerical examples. The first one, we consider the triple well potential at low temperature. And the background of this plot is the potential energy survey, and the darker part represents the lower energy area. And we have two stable state, A and B, where they are lies on the low energy area. And we can clearly see, there's two transitional channels. The first one is go from the top, and the other goes from the bottom. And even though these two-dimensional problems seem simple, but averagely it takes about the model time 10 to 18 to observe one transition. And we can take a look at the learned policy by the neural network, and it will converge to the two kinetic configuration. And we shoot multiple trajectory from these two configurations and get some origin points. And we can clearly see that the origin points bridges the gap between two state A and B, and also shows the transition region. Now, let me show another example. We will study the isomerization of the aldehyde vector in vacuum, and this molecule contains 22 atoms, and its isomerization process can be characterized by the two torsion angles, phi and psi. And the background of first plot is the potential energy surface, and we have two stable state A and B. And if we study from the configuration at the blue point, and then we do the regular simulation, we can only find most of the point at near the region A, but we cannot find any transition to the state B. But with the reinforcement learning, we can find the reaction channels, not only the typical one that's mostly commonly talked about, but also two extra reaction channels that are not often mentioned. And to wrap up, we show an algorithm. Our algorithm is a promising approach to explore the energy landscape. With the reinforcement learning, we have find the kinetic configuration and construct the reaction channel. And in the future, we want our method to apply to more complicated systems. And also, we want to build some algorithm to reduce the cost of getting the reward. And this is my email address. If you have any questions and thoughts, and you can communicate with me later. And thank you for listening.
So thanks, Senwei, for this nice talk. So any questions from our audience? No.
So thanks for the nice talk. I had a question about, you have this proxy for the probability, right? So the reward is not exactly what you want, I think. Is that right?
Yes, because usually the actual reward is the reactive probability is defined with the commuter function, and the commuter function is solved by is the solution of the backward chromography equation. But usually we cannot get the computer function in advance, but we can estimate it using the shooting operator.
So, but can you increase the number of those NAs and NBs in order to better estimate that term, or?
Yeah, usually we can, but we need to increase the N, because we cannot control how many NA we go to state A or B.
And so for everything that you've shown us, you're evaluating the policies with the fixed N?
Yes.
Okay, thanks.
Any more questions? Okay, if not, I think this concludes our morning session. And let's thank again our speaker, Senwei, for the nice talk.